about exponential growth and decay a bit more today. So we've already talked about exponential growth and decay. Today we're going to use it to model real life things. All right, so exponential growth and decay models come in two equivalent forms. You can either do a naught times b to the t or a naught times e to the kt. And a naught is your initial amount, right? And for these two equations to be equivalent, it has to be, right, that a naught times b to the t would have to be equal a naught times e to the kt. You don't have to write this part down. Just kind of follow along, and I'm not going to hold you responsible for explaining why they're equivalent, but I want you to see it. All right, so there's an a naught in both of these, so I can just kind of cancel those, right? So it means b to the t has to equal e to the kt. I'm going to explain it in just a minute. Okay. So e to the kt, I could rewrite as e to the k to the t, because when you raise a power to a power, you would multiply the exponents, which means that b has to equal e to the k for those two to be the same. Right? So b has to equal e to the k, and thus k would be the ln of b. If I wanted to solve for k, I would take the ln of both sides. All right, so for those two equations to be equivalent, b equals e to the k, and k equals ln b. A naught represents your initial quantity, the quantity you have at time t equals 0, which is why we call it a sub 0, meaning amount at time 0. It's a fancy old-fashioned word for nothing. A sub 0, sure. A naught and a sub 0 mean the same thing. Not as in N-A-U-G-H-T, like it was all for naught, meaning nothing, right? All right, B represents our growth or decay factor. If B is bigger than 1, you have exponential growth because you're multiplying by something bigger than 1, right? And if B is a fraction between 0 and 1, you're multiplying by a small number, and we get decay, exponential decay. K represents something that we call the continuous growth rate or decay rate. When K is positive, you have exponential growth, and when K is negative, you have exponential decay. Mm-hmm. That would be impossible. Right. They always go together. Yeah, yeah, because these two are equivalent. So if B is between 0 and 1, K would have to come out negative. And if B is bigger than 1, K has to come out positive. So I think when we do an example, this will make more sense. So here's costs of bottled water. So in 1976, approximately 250 million gallons of bottled water were sold in the United States. So that would be 250 million gallons. Between 1976 and 2000, the bottled water industry had a continuous growth rate. You see that word continuous and you think K, okay? And positive, yep. Continuous growth rate of about 12%. That would be K is 0.12, right? And this is all real data that came from a report to the New Jersey State Legislature. All right, so 1976, 250 million gallons with a 12% continuous growth rate. Nico, what's your question? K is not less than 0, right? 0.12 is bigger than 0. You were thinking of less than 1 with the B, yeah. Yes, or 0.25 billion, yes. So A sub, we're going to let A sub 0, we're going to let 1976 represent time 0 here. So A naught is going to be 0.25 billion. I'm going to write it in billions because this is growth, so it's just going to get bigger. Sure. All right, so I want to write two equivalent models that both represent bottled water sales between 76 and 2000. So because I'm given the K, I'm going to use the model that has K in it first. So it would be the easiest one to write. So it would be F of T equals A naught e to the KT. So F of T equals A naught, which is 1/4 of a billion, so 0.25, e to the K, which is 0.12 T. All right, so there's one model. And then my other model is A naught times B to the T. And the way B and K are related, right, we go up and we say, okay, well, B is equal to e to the K. So if I just in my calculator type in e to the K, that will be my B value for this model. All right, so I've got E, K is 0.12. So e to the 0.12 is 1.1275. So A naught is the same, 0.25 times 1.1275 to the T. So there is my equivalent model, a second and equivalent model. So both of these tell me how many billions of gallons of bottled water were sold years after 1976. So just to convince you that these are equivalent models, I'm going to graph them both and show you that the graphs are identical. So pull up my graphing calculator, go to y equals, and here's model 1. In y1, I'm going to put 0.25 times e to the 0.12x. And then in y2, I'm going to put 0.25 times 1.1275 to the x. And I'm going to have y2 graph in bold just so you can see the difference between the two. All right, what would make sense for a window here? What is x representing? Years since 1976. So I'll go 0 to 24 would take me to the year 2000, so that's good. All right, and then y is representing billions of gallons. And in 1976, how many were there? 1/4. So maybe I'll start at 0, right? 0 billions. And then, I don't know, 3, 5, something, somewhere around there. All right, so now I'm going to graph it. And this is my first model with the E in it, graphing now. And now right on top of it is the bold line, which represents this A times B to the T model. So they are exactly the same. They're exactly equivalent, just in different formats. All right, so I've got two models, different formats, but they will give me the exact same predictions. All right, so the company or the people who did this research, they reported that in 2002, sales of bottled water were nearly 6 billion gallons. So if we extrapolate, that is, use our model to make a prediction, what does our model predict for sales in 2002 and in 2007? Yes, I'm going to go to my table. I'm just going to delete all this stuff out of here. All right, so what should I plug in if I want to know 2002? 26, because 1976 is year 0, 26 years later is 2002. So my two models tell me the same, 5.66 billion. So 2002, my model predicts 5.66 billion gallons. Right? And in 2007, so I should plug in what? 31. I get 10.32. billion gallons. All All right, so let's compare actual bottled water sales, nearly 6 billion in 2002, to 5.66 billion predicted. Not too bad. Yeah, I mean, it's off by 0.34 billion, right? Yeah, 0.34 billion gallons. But 5.66 and 6 are a little bit close, but actual is bigger, right? So this is an underestimate of actual sales. So if you work in the bottled water industry, you're like, great, right? We outpaced the predictions. But if you're the earth, right, you're like, oh, they're doing even worse than I thought they were going to do, right? So our model predicted that we would sell 5.66 billion gallons, and we actually sold 6 billion gallons. So we had an underestimate. All right, so for 2007, we're predicting 10.32 billion gallons. In 2007, we actually sold 8.82 billion gallons. So who's we? The bottled water industry. Yeah. They did not do as well as they had hoped, as well as they had predicted. But the Earth is like, yeah, they're slowing down, right? So we, our prediction was high, right? Which means we're probably not selling bottled water at the same rate we used to, right? It's probably not increasing as fast as it was. All right, so let's use our model to predict when bottled water sales will reach 100 billion gallons. So I can use either equation, right, because these are equivalent. I can use either one. I'll just use this one because it's on the left. 0.25 e to the 0.12 t. So that's my model, and I'm looking for time because they asked me when. Will I reach 100 billion gallons? So I put a 100 over there because I'm already measuring in billions. All right, how do I solve this equation? I can use logs, but before I use a log, I have to do something. Isolate the exponential. So I'm going to divide both sides by 0.25 first. So 100 divided by 0.25, that would be 400, equals e to the 0.12 t. Now I've got a variable trapped in the exponent. I have to chop down a tree and use the log to rescue the variable, right? So I take the log of both sides. All right, so then, yeah, the ln of e to some stuff just gives you the stuff, right? Because the ln of e is 1. So if you bring the exponent down in front, that's one of the properties of logs. When you take the log of something to a power, you can bring that power down in front. So this would be 0.12 t times the ln of e, but the ln of e is 1. So those, yeah, that's just 1. So this is 0.12 t equals the ln of 400. The ln of 400 is just a number, so I'm just going to divide both sides by 0.12. So we get t is approximately the ln of 400. Make sure you close that parentheses, right, and then divide by 0.12. 49.92 years. After 1976, right? So if I do plus 1976, that comes out to the year 2025. So that's my answer. Sometime in the year 2025 is my prediction. But given the fact that we didn't reach our prediction for 2007, this will probably not happen for a little longer, if ever. There could be a bottle industry boom, yep. I don't know. Probably. That makes sense, yeah. And we are, yeah, see, some people claim that they are increasing, yeah. Natural disasters. Okay, so that's our first example. So you can see that there are two ways you can write an exponential growth or decay model. A to the kt or A times B to the t, and they're equivalent. Use whichever one makes more sense to you, or whichever one's easier. In this particular one, they gave me k, so it would be easier to write this model that has k in it. All right, so we also often model population growth using exponential models. So I've picked 6 countries here, and I tried to pick them by taking countries from various parts of the world and countries that have very different rates of growth. It's in the Middle East, yep. It's a very small country. Yep, and everybody's talking about them right now because they're going to host the World Cup. They were chosen to host the World Cup in 2022. 2022. All right, so I started with the United States because that's where we are, right? Our current, or our 2010 population is 309.6 million people. And I looked up its annual growth factor, 1.00969. And all this data that's in the chart, I found in these 2 sites. And data can vary from site to site, so these might not be perfectly accurate. But okay, thank you. I appreciate that. All right, so I've given you current or 2010 population, an annual growth factor, which means that I can immediately write down this model A times B to the t. My A naught is will be my 2010 309.6 times the growth factor to the t. If I wanted to write down the exponential growth model that has e to the kt in it, I would have to change b to a k somehow. And then go back and say, oh, how are b and k related? Oh yeah, k is the ln of b. So if I know b, just take the ln of it and you get k. So pull up my calculator, and I'm just going to hit the ln of 1.00969, and I get 0.00964. So now I can write down my exponential growth model that has the k in it, my continuous growth model. So this would be f of t equals 309.6 e to the 0.00964 t. Does that make sense? Okay, so just looking at these 3 annual growth factors, which of these 3 countries is growing the fastest? Qatar, yeah. What is its percent growth rate annually? Qatar. 11.2%, yeah. So the 1 represents 100%, right? It stays at 100% of what it was, and then it increases by 11.2%. That is a very big growth factor, 11.2%. Good. All right, looking at the next 3, China, Guatemala, and Germany, looking at their K values. Germany's is negative. What does that mean? It's decreasing. Its population is decreasing. It's losing people, right? What does that mean that its growth factor is going to be? Not negative. Close. Less than 1. Yes. When I do e to this value to get b, it's going to give me a fraction. It's going to be a value less than 1. So let's just quickly do that. If I do e to the k, that's how I get b. Oops. So I do e to the negative 0.002, and that gives me 0.998, right? I get a growth factor that's less than 1. which means it's actually decaying. All right, so take a few minutes in your groups to fill out this whole chart. Get all the growth factors, all the continuous growth rates, and all the models. Okay, so let's just look at the graphs together for a minute. Most people figure out which countries go with which, but just so that I can make sure we're all on the same page here. I graphed these models by using the formulas that we wrote in the last two columns. They're equivalent, so you could use either formula, right? So I graphed each of them, and then you can identify some of them based on the y-intercept, right? The A0 tells you the initial amount, and this one that's up at almost 1,300 million, 1,338 million, that's got to be China, right? So this one that has the highest starting population has to be China. And then the one that has the next highest starting population, about 309 million, that's the United States. The only line that's decreasing has to be Germany, so that's this one. Yeah, and then the country that's growing the fastest, right? This one that gets big very fast, right? The population in only 50 years does this ginormous jump, right? That one has to be the one with the largest B or the largest K, right? So which of these 6 countries has the largest B or K value? Qatar. It's got the largest B and it has the largest K, if you figured that out. That means that it's growing faster, right? So a large B or a large K means faster growth. Yeah, so that's a great observation. This place where China and Qatar meet, that's where they will have equal populations, right? So this says that, well, a little after 60 years from 2010, the population of Qatar will be the same as the population of China. Right? And Qatar is a little tiny country. Little tiny country. I actually don't know. Much smaller than China. Yeah, this model is probably not a good model. Yeah. All right, so I have two countries left, Liberia and Guatemala, to label. Which one is growing faster? Liberia, because Guatemala's B value, what was that? Okay. Yeah, so Liberia is growing at 3.5% annually. Guatemala is growing at like 2.5% annually. So Liberia is growing faster. And I can't, if my scale on my graph were a little bit different, I might be able to pick it out by y-intercept, but my scale, I had to make it this big in order to be able to see China, right? So you can't really find the y-intercept of these other two. So we have to look at growth rate, and the one that gets bigger faster would have to be Liberia, and that leaves this one to be Guatemala. No reason, I was just trying to point out which one it was. All right, good. So we can also use exponential models to model decay. And one common thing that we use exponential decay for is something called half-life or radioactive decay. The half-life of a substance is the time required for 1/2 of the current amount to decay, to be gone. Right? So we have two equivalent models, one that has 1/2 as the base and one that has E as the base. And M0 is your initial amount. T is the amount of time that has passed. H is the substance's half-life. And R is the continuous decay rate. And for these two equations to be equivalent, R and H are related by these two equations. In general, just pick the formula that's the easiest, right? If they give you half-life, use this model, right? If they give you continuous decay rate, use this model. There's no need to convert if they, because yeah, it ends up being the same model. Yeah. All right, so let's do an example. We have the burial cloth of an Egyptian mummy. It's estimated to contain 59% of the carbon-14 it contained originally. So this is a common method of dating things that are really old. It's called carbon-14 dating. Organic material contains a certain amount of carbon-14, a radioactive version of carbon. And as organic matter ages, some of that carbon-14 decays. And we know that the half-life of carbon-14 is 5,730 years. So if they gave me half-life, I'm going to use this model. M of T is M0 times 1/2 to the T over H. And 59% is left. If it has 59% now, how much did it start with? 100%. So that's M0 is going to be 100. That's how much I started with, 100%. T is what they asked me, right? So how long? So T is going to stay a variable. Half-life is 5,730. And how long until I have how much left? 59. I started with 100. Well, how long till I get to 59? So I want to solve this equation. What do I do? Divide both sides by 100 first. I want to isolate the exponential. So I'm going to have 0.59 is equal to 1/2 to the T over 5,730. Now I have a variable trapped up in the exponent. Get me down! Cut down a tree and bring a log over, right? Take the log of both sides. The ln of 0.59 equals the ln of 1/2 to the T over 5,730. And that allows me to take this exponent, put it down in front of the log. All right, so now I have the ln of 0.59 equals T over 5,730 times the ln of 1/2. The ln of 1/2 is just a number. The ln of 0.59 is just a number. Yeah, so I'm going to divide both sides by ln 1/2 and multiply both sides by 5,730 to get the T by itself. So we get T is ln of 0.59 divided by ln of 1/2 times 5,730. (4,361 years old). I did, yeah. When I wrote it down, I rounded it to 62. Yeah, yeah, it's pretty old. And that sort of matches when we know that the Egyptians, the ancient Egyptians, lived. All right, so if I want to find the continuous decay rate of carbon-14, that means I want to find the R value that goes in the other formula. And I just find that by doing R is the ln of 2 divided by H. Okay, so R is my continuous decay rate. R equals the ln of 2 divided by 5,730. So 1.2 times 10 to the negative 4 means move the decimal point 4 places to the left. So I have 0.000121. All right, so the last thing we're going to talk about are logistic growth models. So Katrina, you said that this model that we wrote for Qatar is a liar, right? Because the amount of space available in the country of Qatar is not big enough for it to surpass the population of China in 60 years, right? That just couldn't happen, right? We don't have enough space or resources. So a more realistic population growth model is something called a logistic growth model. Growth is always limited because of limited space, limited resources. So logistic growth is used to capture the long-term behavior of a growing population. And it has this general formula, C over 1 plus A e to the negative bt. So it's kind of a hybrid of a rational and an exponential function. And it ends up having a horizontal asymptote that the population grows towards but never passes. And that horizontal asymptote is called the carrying capacity of the environment. So we have initial growth, right? Looks like it's going to be exponential, but then the environment cannot handle that speed of growth, and it starts to slow down and approach a carrying capacity for the environment. And this is the formula we use. We don't necessarily. We can only guess it, right? Unless we've seen a population reach a leveling off. So, I don't know. Mm-hmm. Right, right. But we might have an assumption like that, and it might turn out that that's not true, right? It might turn out that we can squeeze more people than that in. Yeah. Right. We could, because we can always build up. Yeah. So here's an example. The U.S. Census Bureau is currently using a logistic model to predict the world population into the future. Even though, so right now it's about 2000, little after 2010, right? Right now, this looks exponential, right? Just looks like it's going up and up and up. They are predicting that we're going to start to slow down. I don't know if that's a good assumption, a good prediction, but they're using a logistic model to try to predict world population into the future. All right, so I didn't do any examples of calculating a logistic model with you, but I'm going to have you do one in this activity, Learning is Cool. So the first one is about Newton's law of cooling, and the second one is about learning theory. So that's why it's called Learning is Cool. So this learning theory one is a logistic model.